is we're going to take a look at section 21-2. Now, 21-2 is going to be a little bit theoretical also. Okay, not much math in here. So for those of you that are the math gurus here, you're going to have to wait a little more. The next section we'll do a little bit work with math. So, the two things that we're going to do really today are describe the magnetic field produced by the current in a wire. Okay, so we're going to take what we learned in chapter 20 and what we learned in chapter 19 with electricity and now in 20 with circuits, and we're going to relate that to magnetism. So we quickly looked yesterday at what a magnet is, how the poles on a magnet are arranged, how there's north and south. Okay, but today what we're going to do is we're going to take a look at a wire and the current through a wire and how that wire affects the magnetic field around it. Okay? Now, we're going to second explain magnetism in terms of domain theory. Okay, domain theory, which is not difficult. It's not like domain in math and range is different. Okay? Take a look at our first slide here. Okay, the first thing, and this is just a simple fact. A current carrying wire will produce a magnetic field. Okay? A current carrying wire will produce a magnetic field. Just write down the first line for now. Don't write down the right hand rule yet, because I want to talk first. So a current carrying wire will produce a magnetic field. Yeah, and that's what we're going to do right now. So, let's take a look at the images on the left, the two left images here. First, let's look at this one right here. Okay, now, this is a wire running vertically. Now, the wire is going through a table. So imagine the wire comes out of the table, okay? Around that wire, there are little iron like little filings. Okay, what is a filing? Like a piece of like a piece of what? Tin. Not tin, like a shaving, yeah. So imagine like if you had sand, but the sand was all made of iron, like little particles of iron. So these little particles of iron, as you can see here, believe it or not, because of the magnetic field, Jeff, magnetic field around this wire here, have taken this orientation. Can you see how they're circular really? There's rings. There's a ring here. There's another ring there. There's a ring there. And they're taking this circular shape around the wire.
Wait, was the iron in the table?
The iron is on the table, right? And it was in random locations. And we're going to try and do this in our lab, okay? We're going to have a lab like this, hopefully. Where the iron is just randomly spread out on the table. And then the circuit is turned on. So now electricity starts flowing through this wire right here. Electricity flows through the wire, producing a magnetic field around the wire. And that magnetic field is a circular shape around the wire. And what you're going to see here is that the iron filings take on that circular shape because iron is a ferromagnetic material. So it wants to orient itself along the magnetic field line. So that's what you're seeing there. Now, the second image is a compass here. And what we're noticing, and what I want you to do is ignore the north, south, east, west on it. But take a look here. Remember yesterday when we drew a compass needle, it looked like this. And the portion that was colored in like this was the north part of it, and this was the south part of it. So take a look at all of the shaded in portions. Ready? Here, it's facing left. Then it's facing down. Then it's facing lower right. Then it's facing to the right. Then it's facing up. Then it's facing upper left. If I connect these, what do I get?
Circle.
Yeah, you get a circle. Okay? So we see that the north, remember, the magnetic field direction is always indicated by the way the north needle would point. That's what we talked about yesterday. Whichever way the north needle would point on a compass is the way the field is drawn. So here's the north needle, and it's going in this direction. It's going, in this case, a counterclockwise direction. Counterclockwise. Okay? And what this is showing us is that there is a field around a wire, and that field happens to be a circular shape. Okay, it's a circular shape. Now, in a minute we're going to talk about the right-hand rule, but you could already see the field. You could already see the field here. Now, the right-hand rule is simply this. If a wire is grasped in the right hand, so everybody take your right hand. Seriously, take your right hand, put it out in front of you. Okay? Relax. Now, imagine... Not cool. Not cool. Imagine there's a wire in front of you, okay? Now, if the wire is grasped in the direction that the current is flowing with your thumb. So see here, listen guys. The current is flowing up in this wire. You see the eye with the arrow up right here, okay? So So the current is flowing upward. So you face your thumb upward, stop. Okay? Wrap your hand around the wire, and what happens is the directions your fingers curl is the direction of the magnetic field. Okay? So, if the current was flowing down, you would do this. Watch. Stop, guys. If the current was flowing down, your hand would change. So now, the magnetic field would be going the opposite direction. So what this tells us is that the direction of the current indicates the way the magnetic field flows. So when the current was flowing up, the magnetic field traveled in one direction. But the minute the current is reversed, the magnetic field now curls the other way. Alright? So again, the idea is that your thumb faces the direction of the current. The curl of the fingers is the direction of the magnetic field. Okay? So our theory here allows us to say that when the direction of the current is changed, the magnetic field also changes its direction. Okay? Yeah, Max. So again, Max, turn your shirt on. Thank you. The direction of the current indicates the direction of the magnetic field. When that current switches, the magnetic field also switches. Okay? Jeff?
What happens if the current is facing left or right?
So, if you have a wire running left to right, you do the same thing. So you take your thumb, so say the current is running this way in a wire. Your thumb goes here, the curl is this way, so the magnetic field is in this direction around it. Okay? So you should be able to draw a magnetic field around a current carrying wire just by putting your thumb in the direction of current and using your finger curl as the direction of the magnetic field. Grow up, guys. Now, next, we want to look at the magnetic field in what's called a current loop. So imagine you have a wire that loops. So we're looking at the left diagram now. Don't look at the right one just yet. The left diagram. And this looks confusing, but it's actually not. Okay? Look over here at this left diagram right over here now. So, you have a wire. The current is traveling through the wire. Follow on the board with me, please. The current is traveling through the wire. It then goes around the loop, and the current comes back out of the wire. So again, look up at the board, please, here. Okay? The current is traveling in the wire, around the loop, and back out. Use the right-hand rule real quick. Watch what happens. Ready? Your thumb is in the direction of the wire. Then, as you go around here, what's going to happen is your finger or your hand is going to go like this. Okay? So no matter what you're going to get here is this. Watch. You're going to get a curl where the magnetic field is coming up through the loop. You see that? Look at my fingertips here. Okay? The curl is going to be coming up in between the loop or through the coil here no matter what. So the field is like coming out of it. Okay? It's coming out of the loop in the third dimension. So if this were like a wire, and I'll draw it on a flat plane. If this were the wire here, okay, and the current were running in the wire like this, okay, what would happen is this, ready? You take your thumb in the direction of the current, and the field would be coming out of the board. Okay, out of the board, literally. So here's the field, and the field is going like this, and it's coming out of the board from the inside of the loop. On the outside of the loop, it's going into the board. So if I were to draw the magnetic field, and I'll draw that in blue, it'd be coming out of the board like this, inside of the loop, and then into the board when it's on the outside of the loop. Again, because of the right-hand rule.
It doesn't look like, that's not what, okay, so when you go first like this, wouldn't the current be like that?
It is. So in the beginning, the current is just flowing around the wire, around the wire, around the wire. Then it gets to the loop.
What's representing that though?
There's nothing on there. We're trying to look specifically at the loop, Jeff. Yeah. We're looking at, we're honing in on this area right here.
First when it's like upset to sideways, then it's just like...
So it's just flowing like this, yeah. Then it turns, right?
Yeah.
And as it goes around this loop, no matter what, inside of the coil, inside of this coil, it's coming out of the page, no matter where it is. Because it's like this. Watch my hand. Watch the current flow. So no matter what, my fingertips are pointing out of the board. So inside of that coil, you have this magnetic field coming out of it. Okay, coming out of it. Now, that is analogous to a magnet. And if you think about it, take this and turn it this way. This would be like, see, and this is a bunch of coils. See all these coils wrapped around one another over here? We're going to talk about this called a solenoid. But there's a bunch of coils wrapped around each other here. And if you think about this one that we started with over here, This is like taking this coil and just having a bunch of coils on top of each other like that. And the solenoid produced would look like this. Okay? That's what the solenoid would look like if you had a bunch of those loops connected to each other. And what happens is the current flows into, or the magnetic field flows into this coil and it would come out the other end. So this is what the magnetic field would look like over here. It would come into it like this from the bottom and it would flow out the top, which is the same thing if you look at it as a magnet really. Take a look at this magnet on the right here. From yesterday we talked about the magnetic field leaving the North Pole and entering through the South Pole here. It's the same thing as this diagram. Okay, so what a solenoid is, we're going to talk about a solenoid next. A solenoid is one of these loops, but repeated over and over again. Okay, and a solenoid acts like a magnet. It acts just like a magnet. Okay, Jeff?
Technically, those lines are going all the way around, right?
What do you mean?
It's like see those north? They're really going.
Yeah, they're looping all the way around. Yes,
Okay.
yes,
So
absolutely.
It always goes north to south.
Yep.
It's like looping that, so like there's 2 rings this way, that's what we see. And then there's another ring going this way.
Yeah, because I'm trying to figure out how to
So it's just rings around.
It's really a three-dimensional. Olivier is making a good point. If you have an actual, say this is the magnet right here, okay? There are field lines going like this. Ready? From north to south and north to south, but there's also north to south towards you, north to south toward me. All that matters is that it's going north to south. So in three directions, in every direction. Yes.
It's 4, right?
What's that?
Or 3.
Yeah, you know, well, I mean in 3 dimensions, yeah, in 3 dimensions.
4 directions.
Well, infinite amount of directions, right? Because it can go in any orientation,
Yeah.
right? In all 360 degrees, exactly. The idea, though, is this, again. When you have a coil in a wire that repeats itself over and over again, it's going to cause this magnetic field to flow through the coils. This is the key here. It's flowing through the coils, which makes it act like a magnet. Just like a magnet. Okay? We're going to talk now specifically about solenoid. Okay? So a solenoid can be defined as a long, helically wound coil of insulated wire. A long, helically wound coil of insulated wire. Hey, why does the wire have to be insulated? Who can answer that question? That's a tough one. Why does the wire have to be insulated? There's really only one answer here. Max?
Because it needs to maintain a certain heat.
No? Good idea, but no, that's not it. Good idea. Other ideas, Olivier? No? Sure, yes, theoretically, but no, that's not the reason. That's a safety precaution. Because what?
The current would just flow straight through.
Yeah. If they were all touching, right? Think about it. If 2 wires are touching, that creates a short. So if all these wires were touching and there was no insulation, the current would go in this end of the wire, right? It wouldn't actually flow through the coils. It would flow right across the surface and out. That's what would happen. If all these wires were touching, it would be like it was just one wire, right? If there was no insulation, it wouldn't flow through all those loops. Okay? It would jump across the surface because there's touching. It's a conductor. Good point there, Stash. What is the red thing I just drew?
Is that the solenoid?
What I just drew would be what the current would be. Okay, if it was not insulated, that's what I drew. This device here with these wires looped with insulation is called a solenoid. Yes. Okay. Now there are some key points about a solenoid. First, as the current increases, the strength of the solenoid increases. So that is what related? That is blank related. What's the word to fill in the blank? Thank you. Directly related or proportional. Very good. That's like 2 scenarios being similar to each other. So, as current goes up, solenoid strength goes up. Solenoid strength. And the solenoid strength is really the strength of the magnetic field it's producing. Okay, but we can say the solenoid strength. Second.
And it's not a magnet that acts as if it's a magnet.
It acts like a magnet. And in a minute we're going to talk about something called an electromagnet. Okay, so hold on from that one. Second thing. The field or the solenoid strength is also proportional to the number of coils per unit length. So the more coils, the more strength. Which is logical. Think about that. The more coils you have, the more magnetic field you have together. Right? Each coil produces a magnetic field around it. The more coils you have, the more magnetic field you have. The sum of them is a larger quantity. Okay? Again, the more coils, the stronger the solenoid again. Third key fact. The magnetic field inside of the solenoid is uniform. And you can see that in the diagram. Take a look. From the south end all the way to the north end, these field lines are coming in parallel fashion. Okay, and here they're in parallel fashion here. Not parallel like circuits, but I mean parallel to one another. Okay? But outside of the solenoid, take a look at the field you have out here. Okay? These are non-uniform, and much weaker. So the field inside of the solenoid is uniform and strong. The field produced outside of a solenoid is weak and non-uniform. Hey Jack, question for you. In cars, I know solenoids are used with engines and motors and stuff. Have you any idea as far as, have you had any experience with this yet?
Good one, Jeff.
With solenoids and
Yeah.
No.
Okay.
Can that be like the suspension?
Say again?
Can that be in the suspension system?
No, it's usually run when it comes to like a motor or something that's turning.
What
Not a
about
solenoid.
like the spark plug or something? Nah.
I don't know much about it.
No, I'll Google. Do you know they make guns out of this now? They're trying to make a gun with like magnets lining the inside.
Oh,
of the
I
barrel.
wanted to talk to you about that.
When it fires, it's like
So it's an extra push
it
almost.
increments it,
Have you
and it
seen?
like leaves the bullet, and it's like completely silent.
Interesting.
Have you seen the news called look up the Chevrolet Eco. Jack, what's that? There's a car that uses its momentum to save gas and energy. The Volt. I don't think it's the Volt, but it's a Chevrolet
Really?
Eco something.
It harnesses the energy from its momentum?
Momentum. So as you're going on a hilly thing, like you will use like a substantial amount of less
Well, you know,
energy and gas because it uses the momentum.
that's really cool. And when I was at Villanova, one of the senior design projects was a backpack that, because of the motion of movement, because it's a very hilly campus, moving up and down, it actually harnessed the energy, and it was able to charge something in your bag.
Then it would like give you momentum.
No. So it took the energy of the motion that you're moving with, and it harnessed that into a battery, which could then charge like your phone in your backpack while you're walking.
There's like things like that where you put like a hot mug
Yes.
on a thing, and
Yes. And it's the same idea as it's a generator in a sense. It's when you like crank a flashlight, right, to power it.
if you go on Kickstarter, you see a lot of those things. That's
Ah, cool. Very cool. All right. Next.
Whoa.
Now, an electromagnet. An electromagnet is simply adding an iron rod through the center of the coils in the solenoid. Again, if you took like say for example a nail, okay, we're talking like maybe like a 3-inch nail, one that would be used for like housing and putting up foundation. Now, you take a nail and you put it inside of a solenoid, okay, it creates what's called an electromagnet, okay, an electromagnet. And what it does really is this. Remember we talked about how something that is made of a ferromagnetic material can become a magnet under the influence of other magnets. So, if you put a material in a magnetic field that is not necessarily magnetic, you can have an induced magnet. And that's where we talked about hard and soft magnetic. So what's happening here is this. You're putting an iron rod inside of a solenoid. Inside of a solenoid, there's a magnetic field. So that's going to make that iron rod itself magnetic, which will then give off its own magnetic field. Okay, it's going to realign the north and south poles in that iron rod to make it magnetic, which then gives off its own magnetic field, which makes this overall field of the solenoid even stronger. So by putting an iron rod through there, it induces a field on the iron rod, it makes it a magnet, which produces its own field, which adds to the field that already exists on the solenoid. So it strengthens the solenoid in the end. It strengthens the solenoid. Okay? Because what you're doing is you're creating another magnet inside of the solenoid. Inside of the solenoid. Okay? Because there's a current running over that wire. And this is an example of yesterday. I said hold off. The question was, what types of ways or what ways can you induce a magnet or a magnetic field on an object that's not magnetic? This is one of those ways. Okay, so you take an iron rod that is not magnetic, put it in the center of a solenoid, it will induce a field on that and make it magnetic. Okay, and make it magnetic. All right.
And increase the magnetic field.
And in the end, increase the magnetic field that the solenoid provides. Okay, because now this is like adding to the solenoid. It's making it stronger. The last thing I want to go over for today is the idea of how this actually works. And this is where magnetic domain theory comes in. And I'll put up an image, and I'm going to talk for a little while. If you want to read the notes, and the notes have a very good description in a paragraph form here. Okay? If you want to read the notes, you can do that. Okay, feel free to. But I'm just going to talk now. And here's what's happening. Inside of an unmagnetized material, there are what's called magnetic domains. And those magnetic domains are not aligned. That's what you're seeing on the left-hand side here. So inside of a material, these are on very small levels, like 10 to the negative 4 meters. Right? So on the left-hand side here, you're seeing a material that is not magnetized. And the arrows are pointing in the direction of the north pole of that material. So each of these domains has a north and south. So this is pointing in the north direction, pointing in the north direction. So all of these are pointing in the north direction. But they're not aligned. They're completely random. So as an overall object, there is no net north and south pole. Because they're all like counteracting each other. And it has to do with the electron spin, really. Okay? And it's a little more quantum physics than anything else we've done this year. Okay? So there's no net north and south pole on an object like this. Because each of these are pointing in different directions with their north and souths, which are counteracting each other. Okay? But when an object is in and is under the influence of a magnetic field, that object's poles align. And this is what happens. They all go in the same direction. So you don't even see the breakups here. See how you see these little boundaries on the left-hand side? You see these boundaries here that separate all of these magnetic pieces? Now they all align themselves in the same direction because they're in a magnetic field. So it looks as if it's only one domain. Okay? So all these little pieces realign themselves to become one object that is magnetized. Remember what these are called? Anybody remember the term when they have different poles at the end? We use the term. I used it really briefly. It's called dipoles. Okay, I mentioned it real quick with electricity, but these are dipoles, okay? Because there's a north pole and a south pole, but this is one giant dipole now, which is what a magnet really is.
Is there like any reason why some of the things in the some of those arrows don't have like ends on them, like on the other side?
Where are you at?
On the right, there's
It's
one.
just some
It's just printing arrows on it.
Yeah.
I guess, yeah, I don't see any. Where do you see that?
There was
In the
one
right-
with
in
just
the right
an,
picture,
I mean,
there's-
just an arrow.
Yeah, there's just random little
Dots.
arrowheads.
Here?
And then one
A
of
little
them.
higher up.
I see like 4. There's one.
Higher up. There it is.
Yeah, it's just,
There it is.
yeah. I remember, guys, all your images I either pull out of your textbook or I go online and I actually search for good images. So it depends. Yeah, those random arrowheads by themselves, I don't know. It's just a typo.
Do you scan the text?
No, I have a PDF actually of it. So I'm able to access it on my computer and then just copy an image right out of the PDF. Snipping tool.
I have
Just pull it. It's actually it's a different edition of the book. It's not the same edition. So the page numbers are totally different, but the topics are usually the same. The pictures change from year to year, but that's good because some of these pictures aren't in your textbook. So I'm able to pull them out of the old book or the different edition book. Actually, your book is the old edition. There's a newer edition that's out, but there's a new edition that's going to come out in a year or two. So we're waiting to get new edition books. We're going to keep using the ones that you guys have for another year.
Can we go over questions on the test real quick?
Yeah, absolutely. Tonight, what we're going to do is this. There's 2 pages. Just read through them, please. Okay, it's actually pretty interesting stuff. Okay, read through these 2 pages. It's an application of what we're seeing here.